All right. Now let's look at an application problem. Say we have this temperature function t depending on three coordinates x, y, z. And you can see that the temperature gets really decreases really fast if x, y, z actually are increasing, right? Because in the denominator. So you can imagine this is the temperature in the atmosphere of the Earth, and x, y, z, these are three directions. Okay, so first one, find the rate of change of the temperature at the point 1, 1, negative 2 in the direction of 2/3, negative 1/3, and 2/3. Now, just look at this vector v over here. This is specially chosen so that it's going to be unit vector. If you look at this one over here, what's going to be v's length? We will see that's going to be 4/9 plus 1/9 plus 4/9. Square them, right? It's v dot v. And that's exactly 1, right? This is exactly v dot product v. So that's fine. But that means we do have a unit vector over here. And make sure of that, because otherwise the directional derivative won't be right, because if you have a scale that's not 1, then you are not going to get the right derivative. Okay, so now we're going to find first three partial derivatives. So tx is going to be equal to, remember this is the denominator, so we have the whole thing over here squared is 1 plus x squared plus 2y squared plus 3z squared and negative. And then by chain rule, this is 2x, right? Ty will have the same denominator, negative 1 plus x plus 2y squared plus 3z squared and squared. And this is going to be 4y. And the third one too is going to be negative and the same denominator, 1 plus x plus 2y squared plus 3z squared and squared, and then we have 6z over here. Okay, so these are three components of the gradient vector, and then we need to evaluate it at a particular point. So at this point, 1, 1, negative 2, we have this gradient vector is equal to, we will see that denominator is 16 squared. It's negative 16 squared, and the top is 2x. X is 1, so we have 2. And then the second one, we have y is 1, so we have negative 4. Again, 16 squared. And the last one, again, but negative, negative, now we have positive. So we have 12 over 16 squared. Okay. And that's the gradient, three partial derivatives. So now, how can we find the rate of change? The rate of the change in this direction, this is a derivative, so d, v. Now, let's be very careful because we are talking about the rate of change, so it can be actually negative and it can be positive. So let's not take the absolute value. Just take the derivative of this t in the direction of v. So that's exactly what we have over here. We can say that's going to be 2/3 tx minus 1/3 ty, and what we have over here is plus 2/3 tz as well. So if we multiply them out, then we're going to have negative 4 over 3 times 16 squared. We add them up, so the second one, negative 1/3 ty, negative 4 over 16 squared. So let's just copy this one first. And then plus 2/3 times 12 over 16 squared. Okay, so now let's do some simplification over here. So add them up, and this is going to be equal to negative 4 over 3 times 256, and then plus 4 over 3 times 16 squared. And then we see these two terms actually they cancel. And then look at the last one. So these two again cancel, and the plus, we will see this is going to be 8 over 16 squared. So that's what we have. We have 1/2 times 1 over 16, and it's 1 over 32. So that's the directional derivative. In fact, we can see the temperature is increasing because this one is positive, right? So in this direction, temperature is gradually increasing at the speed of 132 units per second if we have time. Okay, so this is the directional derivative. All right, it can be any direction and we can find them. All right, so now let's try to solve the second part of it. At this point, we can easily see that the directional derivative depends on the direction, right? We multiply this direction over here to 3 components of the gradient vector. So in which direction we are going to have the temperature increase fastest? We want to do the following thing. We want to have the following thing, that we want to find direction v so that when this one over here is maximum length and also positive. Okay. And it's just the direction, so it has to be a unit vector. Now, we know that which direction we're going to have. So we know that this v over here must be proportional to this gradient. And also we want this v over here to have 1. Okay. Now to have a positive 1, that means we will have v precisely to be the gradient vector unit vector of this tx, ty, tz. Now, because we want the unit vector, so we can throw away the common factor. So we will just use this one over here. We're going to use, you can just use -1 and -2 and 6. Okay, but this one over here is not on the unit vector yet, so we still need to normalize it. Let's call this vector A over here. Okay, so what's going to be A's length? That's going to be 1 plus -2 squared plus 6 squared. So this is going to be 1 plus 4 plus 36, and it's going to be 41. So the length of this vector is going to be 41. So now we have the unit vector. So v over here should be equal to -1 over root 41, -2 over root 41, and 6 over root 41. And in this direction, dvf dvt is positive and has the maximum length, maximum magnitude. What it means is that in this direction, the temperature is going to grow fastest. All right, that's all for this section, essentially. It's section 12.6.